These are examples for section 13.1, area of triangles and parallelograms. Example 1. What is the area of each parallelogram? Parts A and B. Recall that when finding the area of any parallelogram, we can use the formula base times height, or BH, where base and height are always perpendicular to each other. That's true in any figure. The base and height must be perpendicular. Part A. Here we have a parallelogram where they give us the length and the width, and then they give us the height or altitude. Recalling that the height and base must be perpendicular, the base would be 5 inches, one of the sides of the parallelogram, and the height is 4, not 4.5, because 4 is perpendicular to the base. So the area is base times height, where B is 5 inches, and H is 4 inches. So using the formula, we have the base, which is 5 inches, times height, which is 4 inches. When we multiply these together, the numerical parts, we get 20. Multiplying inches together, inches times inches, we get 20. Inches times inches is inches squared. Inches to the first times inches to the first is inches to the second power. This is how we get square units in area. Part B. Find the area of this parallelogram. Turn the video on pause and turn it back on when you're ready. In this parallelogram, using the formula A equal base times height, where B is 2 centimeters, and H, which is 3.5 centimeters. Because the base and height must be perpendicular, many times in our figure the height has to be used with the base extended so that there's a right angle. So the area is, using the formula and substituting in the values, 2 centimeters times 3.5 centimeters. Multiplying those together, we get 7.0 times centimeters times centimeters. Centimeters times centimeters is centimeters squared. So 7 square centimeters is the area of this parallelogram. Example 2. For parallelogram ABCD, what is the length of DE to the nearest tenth? It's right here. Well, DE is perpendicular to AB. AB is a base, and DE is a height. The problem is we don't have the area. If we had the area of this figure, we could find the height having been given the base. So we have to look for another way to find the area. As soon as we do that, then we can use area and this base to find the height. So we look around the figure and see if there are any other indications of any other bases or heights. You'll notice that if we use this as the base, is perpendicular to FC, and that's the height of the parallelogram. The base is not at the bottom, but yet it's still the base. So we could use area equals dA for the base times FC for the height. And we've got numbers for both of these, so we can find the area. So we do this first. First, find area. So the area is dA, which is 13, times FC, which is 9. Multiplying those two together, we get 117, and these are in inches, so that would be square inches. Now that we have the area, we can find DE by using this as the base, and this is the height, now that we have the area. So using the area formula, A equals base times height, just like we did here, except with two different values, we have the area, which is 117, equals the base. This time the base is AB times the height for this base would be DE. So that's 117 equals AB, which is 9.4 inches, times DE, that's what we're looking for. And then by dividing both sides by 9.4, we can solve for DE. When you divide, you get an approximation. Rounded to the nearest tenth, we get 12.4. And this is square inches. Oh, inches, not square inches. This is the height. Example 3. You want to make a triangular sail like the one at the right. About how many square feet of material do you need? Round to the nearest tenth of a square foot. Now in this particular problem, of course this represents a triangle. It almost is a triangle. And they give us the base, and they give us the height, one of the heights and bases of it. The problem is we have everything in feet and inches here, and they want everything in square feet only. So the first thing we need to do is convert to all feet. To do that, let's take the base first. Base is 13 feet 4 inches. To do that, to put everything in feet, we just take the inches, 4 inches, and multiply by the conversion factor for feet and inches. There are 12 inches in a foot. We put inches in the denominator so that it will divide out with the inches up here and feet up here in the numerator. Again, 12 inches for 1 foot, so 1 foot over 12 inches. The inches divide out, and we're left with 4/12, which reduces by 4. 4 goes into 4 once, 4 goes into 12 3 times, and so we get 1 times 1 foot is 1 feet, or 1 foot, over 3. So 1/3 of a foot, which is exactly 0.3 repeating feet. So there is our feet. Now we add it to the 13 feet. 13 plus 0.3 gives us 13.3 repeating feet. So we'll use that. For our height, do the same thing. We have 12 feet, 2 inches. We use 2 inches. We multiply by the conversion factor to get rid of the inches in the numerator. We put inches in the denominator. That's 12 inches for 1 foot. So then we get inches divide out. 2/12 reduces by 2. 2 goes into 2 once. 2 goes into 12 6 times. 1 times 1 foot is 1 foot over 6. 1/6 of a foot. When you divide that, you get an approximate. This is approximate also. 0.16 repeating the 6 feet. We add that to the 12 feet. 12 plus 0.16 repeating gives us 12.16 repeating feet. So this is our base, this is our height, and specifically feet. Now we find the area. Area formula for a triangle is not base times height, it's half times the base times height. Since we have decimals, we're dealing with decimals, we can change everything over to decimals. 1/2 is 0.5 times the base, which is about 13.3 repeating feet, times the height, which is about 12.16 with the 6 repeating. When you multiply that in your calculator and round to the nearest tenth, we get about 81.1 square feet. So the amount of material they need for the sail is about a little over 81 square feet of material they're going to need for the sail. Now later on we're going to learn how to do this without having to approximate, where we find the area first and then we change square feet or square inches into square feet. Example 4. Write a formula that will help you find the area of the composite figure at the right. Then find the area of the figure. This is a composite figure because there's two or more figures that are placed together and not overlapping necessarily, and they are asking us to find the complete and total area of this entire figure. Notice, first of all, which figures we have. We've got one parallelogram, we've got two triangles. Notice that the two triangles are congruent triangles. 3 centimeters, 3 centimeters, they're both right triangles. This is 4 centimeters. This would be 4 centimeters also because this is a parallelogram and opposite sides are congruent. So first of all, get a working model for your area of the composite. So the area of this composite is going to be the area of the parallelogram right here. Then we're going to add the area of one of the triangles. Since there's two that are congruent, we multiply that by 2. Once you get a formula for your composite, a general formula, then it's time to define variables. Starting with the parallelogram, we have base and height. We need those to find area. So for the parallelogram, we have base, we have height. The base of the parallelogram is 4. The height is 6. For the triangle, for either one of the triangles, just take one of them. The base would be 4, and the height of the triangle is 3. The base is 4, and the height is 3. Then the next thing you do is you go through and see what similar dimensions that these two have, or that they share. Notice that the base of the parallelogram and the base of the triangle are the exact same thing, 4 centimeters. So when we come over here, we can call this base, instead of bases, we can call them base 1, both of them, because they're the same thing. The height of the parallelogram, however, and the height of the triangle are different. So I'm going to call H6 H1 for the parallelogram, and I'm going to call the height of the triangle H2 since it's a different height. Then we take our formula here and we write a more detailed version of it using the formulas we know for parallelogram. A equal BH, and for a triangle, A equal 1/2 BH. So starting with the parallelogram's area, that's base times height, and since this is the parallelogram, both of them are B1 and BH1, but our 1's in, plus 2 times the area of the triangle, one of the triangles. The height is 3, the base is 4, but we have 1/2 in our formula. So 1/2 times the base times the height. Well, the triangle's base is still B1, and the height now is H2. So this is a working formula. We want to simplify the formula as much as we can algebraically. So one thing we can do is, since 2 times 1/2 divide each other out, we now have B1 H1 plus 1 times B1 H2. These disappear. Then notice both these terms have a factor in common, B1, here and here. So if we factor out B1 from both these terms, we're left with H1 plus H2. These are now gone. They're right here. So this is a formula for the composition of this figure right here. The second part was that they wanted us to find the area itself. So we plug in our values or substitute them in. B1 was 4 times H1 was 6 plus H2 was 3. The math here is relatively simple once we got our formula simplified. 4 times 6 plus 3 is 9, and we get 36 square centimeters for the area of this composite. Example 5. The area of triangle DKJ, or find the area of triangle DKJ in the coordinate plane of figures. When it comes to coordinate geometry, we can find area also. We still use the same formulas, however sometimes we need to use some of our formulas for the coordinate plane in different situations. Distance, midpoint, slope. However, in this problem, they're asking for the area of triangle DKJ. DKJ, this one right here. And so we need the area of a triangle, which is 1/2 base times height. Base and height are always perpendicular. So find a base. The most obvious base to use here would be JK, because if we use JD, we're going to have to find the length of that using the distance formula, or if we use the length of KD. So it's going to be a lot easier to use JK and use the ruler postulate. So our area is going to be 1/2 times JK, which is the base, times the height. Well, the height, it has to be perpendicular, so we're going to have to use this length right here, from this point down to D. I'll call this point A, just for lack, oh, there's already an A. How about we call it M? So MD. This one's relatively easy because we don't have to use the distance formula or the midpoint formula or any of those. So to find the area in our units here, we use the ruler postulate for JK. Count them: 1, 2, 3, 4 units. So the base is 4 units. And the height of the triangle then would be 1, 2, 3 units. So for our area formula, that's 1/2 base times height. We have the area is 1/2 times the base, which is 4 units, times height, which is 3 units. Notice that 1/2 and 4 will both divide out. 2 goes into 2 once, 2 goes into 4 twice. Now we have 1 times 2 times 3, which is 6/1, or 6. Now this is 6. These were square units. We don't have any specific name for these, so we just call them units. So we have 6 square units for the area of this triangle right here. You can also write 6u squared, and that's okay too. Example 6. Find the area of triangle DEF. Round your answer to the nearest tenths place. Sometimes we are not provided a height to use in a figure along with our base. When this happens for the triangle, you already know from our right triangle unit that we can use the law of sines and cosines. There was a formula that we can use if we have one of the angles, but we don't have any of the angles here. So how do we find the area of a triangle when only given 3 sides and no angles, no angle measures? Well, we can use Heron's formula. As we discussed in the notes, Heron's formula has 2 parts. The first part is used in the second part. So the formula actually for Heron is A equal to square root of S, which represents the side length of the triangle, times S minus A, times S minus B, times S minus C, where S is equal to 1/2 times the sum of all 3 sides. So generally we find S first. Once we find S, it'll be one number, and we can substitute it into this formula and find the area of our triangle. So starting with this one right here, S is 1/2 times, and I'm going to assign values for all 3 sides. It doesn't matter which 3 sides you assign A, B, and C to. I'm going to let 28 be A, 15 be B, and C is 17. So we have A, which is 28, plus B, which is 15, plus C, which is 17. Before we can take half of that, we need to add those together. So we sum those up, and we get 60. So 1/2 of 60, or 1/2 times 60. 2 and 60 are divisible by 2. 2 goes into 2 once, 2 goes into 60 30 times. So S is 30. Now that we've found S, we use that S in this formula, here, 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 and here. So A, the area, is equal to the square root of S, which is 30, times the difference between 30 and the first side, 28, times, that's times there, not plus, S, which is 30, minus B, which was 15, times S, which is 30 again, minus C, which is 17. Then we get the square root of 30 times 30 minus 28 is 2, times 30 minus 15 is 15, times 30 minus 17 is 13. Then we get A is equal to the product of all four of these. 30 times 2 times 15 times 13 is 11,700. Once you get to this point, you approximate by taking the square root of 11,700 in your calculator. That's not a perfect square. We get 108.2 square centimeters. So the area of this triangle in square units or square centimeters is about a little over 108 square centimeters. Example 7. In a parallelogram, a base and a corresponding height are in the ratio of 5 to 2. So, in this parallelogram, whatever the length of this base is, and whatever the length of the height is that's perpendicular to it, is in a ratio of 5 to 2, base to height. So base to height is 5 to 2. What that means is that whatever the base is, it's got a factor of 5 in it. Whatever the height is, it's got a factor of 2 in it, and the other factor is common to both the height and the base. So first, we let x, some variable, equal a common factor for both. We were given the area, which is 250 square centimeters. They're wanting us to find the lengths of base and height. So since we have the area, 250 square centimeters, we will use the area formula for a parallelogram, which is base times height. Be careful, if you're using a triangle, don't forget the 1/2. This is a parallelogram, so it's just base times height. Well, the area then is 250. The base, then, if x is a common factor to both, and it's got 5 as a common factor, the base then will be 5x, or 5 times x. And the height, since it's got 2 as a common factor, will be 2x. Then we plug those in, or substitute those in for b and h, base and height. So we have the base, which is 5x, times the height, which is 2x. When we solve for x, we'll have our common factor. Then we can substitute those back into here and here to find the base and height, the actual base and height. So solving this equation, we have 250 equals 5x times 2x times is 10x squared. Divide both sides by 10, and we get 25 equals x squared. To get rid of the square, we take the square root of both sides, and x squared, the square root of x squared is x, and the square root of 25 is plus or minus 5. Of course, negative 5 won't work because it'll give us negative values for lengths, so just 5. We use that 5 now to find the base, which was 5x. 5 times 5, x is 5, is 25. So 25 centimeters is our base. We know it's centimeters because the area was in centimeters squared. And the height is 2x, or 2 times 5, which is 10 centimeters. And there's our height. So this parallelogram's height is 10 centimeters this way, and its base is 25 centimeters this way.